Right, so now we have gone through the circuit analysis stuff. Next part is actually, I will show you some hints on the exercise. So today's the theory part was quite short. It's 1 hour, but well, now you have a couple of hours of working on the exercise, and I will be hanging around during that time. Anyways, so the circuit analysis is simply solving the unknowns on different circuits, and if you open the exercise template, basically there is your, well, quite familiar circuit. You already did some measurements on Tinkercad on the same circuit. So today's the circuit analysis exercise is basically doing the theoretical analysis, mostly theoretical analysis for that one. And to do, so first part, so there are 3 parts. First part is analyze the circuit in schematic 1 theoretically and determine the values on the following table. And practically there is the comparison to the measured values. You can either use your previous exercise values here, or if you didn't do that part, then this is a time you actually do the measurements. And answer with explanation means that you need to show how you calculated it. So if you use, for example, Python there to solve everything at the same time as I did there, so then basically you might add some the Python commands here. So practically similar things what you need to show for the math or physics teacher, that you have done the calculations, not just found a value somewhere. So not guessing, but showing that you have done it. So first one is determine the total resistance of connected resistor between points A and B. Okay, so total resistance between A and B. So that resistor network here. Okay, if you measure that one, you should have taken out the this power supply for the measurement of that resistance. But for this exercise, you can use either these parallel series resistors, or just calculate the current, solve the current, and you know the voltage. It's up to you how you do it. So there are plenty of different methods to do this exercise. Then determine total current drawn from the battery. Well, that's not a biggie if you know the total resistance of the connector resistors between points A and B. And then compare it with the measured value. Then third one, then determine the current from C to D using Thevenin's model. This is what I recommend actually. Okay, let me see if I can actually open that one. No, I cannot. Oh, maybe I can actually. Let me open that one also on another window to show this, and then we have that. So practically speaking, oops. Of course it I hate when this. Okay, the other one is very tiny picture here. So the Thevenin's model here, you have basically 2 systems. you can consider this as two separate systems. One which has voltage supply and these resistors R1 and R2 only. And the other one is the system with the same voltage supply U and R3 and R4 only. Okay, and basically those two separate systems are connected with wire between C and D. So the question is how much current flows through from point C to D, that wire. When you do this Thevenin's model, it's quite fast to calculate. If you do everything right, it's quite fast to calculate the current from C to D. And I think you already have done the measurement on the previous exercise between the current between C and D. Okay. Let's go a little bit forward. So these are practically theoretical calculations now. Part 2 has a combination of measurements and theoretical calculations. So basically theory is not just for theory. It's not just for the circuit analysis of unknowns that you actually don't want to know, but it also helps you to understand why you cannot put just any load to some microcontroller pin. So determining how much current Arduino IO pin can source and sink. Okay, source meaning that you are driving a positive output voltage to ground. So its current basically flows from the device to the load. And the sink meaning that it sinks current which flows from higher potential down through the processor. Okay, but anyways, Thevenin's model. That's simple. Thevenin's model is Thevenin's model. And we have a quite complex integrated circuit now in our hands. So how does this circuit analysis help us now? So few things you would do. So connecting a resistor between an Arduino Uno IO pin 8 and ground. Make a program which turns the output to high state and keeps it there. And basically then you can start adjusting resistor value and observe the output voltage. Okay, practically what this is all about is the same what we did on the first week on paper, or I actually just mentioned that one on paper. Let me see if there was the theory correct. Yes, correct theory, fundamentals. And well, there are way too many values here, probably what you measure here, but first one is the we start with this we start with okay we start with the open circuit voltage, then we don't determine the short circuit current, but we do it. Okay, let's see how to avoid smoke method. Open circuit voltage without the load, then replace the load with a known resistance value and we start with big value. So, okay, there we go. We start with the big value. Like 100 kilo ohms. Oops, that's small again. Well, can I actually? No, it doesn't. Do I have way to? No. No, it doesn't expand that one either. Okay. But anyways. Let me close that one. That was totally useless. So we start with the big value, and basically we get enough of the change in voltage, big enough voltage drop that we can actually start doing calculations with some accuracy. If you have 0.01 volt voltage drop, it has about 100% the relative error. So think of what the physics teacher usually teaches on the first classes is the accuracy of the measurements. So you need to have big enough change in order to do any measurements. But anyhow, when you have done basically the loading the output enough, meaning the small enough resistor which has a higher enough current, and then you have found a decent voltage drop, then you can actually start doing the calculations. And using the previous measurements, determine what are Thevenin's model parameters. And basically, okay, let me show what I'm talking about in here. So we have Thevenin's model. Like this, and this is the question mark, and we have the known load, and when we have good enough the voltage drop here, which you are actually measuring, then this voltage drop across R2, maybe I should actually mark it with red, voltage drop across R2 is same as that VCC minus V out. And the current actually is the same as what flows through this load resistor here. Okay, and that actually should give you pretty good the guess or guesstimate what are the internal voltage value, and then there is the internal resistance for the Thevenin's model. Okay, now that part is done. Next, we use those values. Okay, so-called TTL logic levels, which are standard for any, say, if the voltage supply is above 3 volts, then the logic levels, they mostly follow these rules that the high state is when the voltage is above 2 volts. That's high state. And then what you need to do is to determine how much you can now load the output in order to actually maintain that high state, meaning what is the minimum resistance value that you still have above 2 volts in the output. And okay, you can calculate it here. I also recommend also to try it since you have the circuit diagram or the Tinkercad running, and you can basically then also measure that you got just about the right value there. The measurement and this theoretically calculated should be pretty close to each other. If not exactly, they should be within, say, few percent error margin. If you get totally different values, then you have done something wrong. Usually on the calculations, the measurement part is usually quite easy. Okay. So basically determining what is the maximum current the device can source and still maintain the high state. And then also the, okay, you need also the maximum current. The Armin is there, but it's also asking about the current, so you might also add that. Oh, was it here? Oh yeah, it was here. It's just on the 2 pages. So maximum current as a source, Imax, and then minimum resistance, Armin. And again, remember to explain. If it's just an answer without any explanations, then it's no points. Then the 7th part, as you can see, there are plenty of things to do, but they are relatively small things. And just as a reference, if we had real laboratory experiments, this would take, the laboratory itself would take, from the faster ones, it would take 1 hour, and the say in average it would take about 2 hours, and basically in 3 hours everyone would have been done with the exercise. So this is basically which file is open. It's not actually, it's basically the assignment. Assignment number 3 is open. It was published yesterday. So, okay, so that was the solid high state. Let's think of the other way around. You can also load the or use the output as the pull down kind of the output. So basically you have the load is between the high 5 volts and the output. Why to do it like this? Well, sometimes it's better. Sometimes it's just better to drive the output as a so-called open collector or such. Some processors actually prefer that they are used this way, and some processors, the older ones, you cannot do anything else than open collector. There are some, say, reasons for that one. Basically, how simple you can make the this Arduino output gate. Okay. So, okay, the 5 volts, or no, not 5 volts, but in order to have the high state, you must have at least 2 volts at output, or actually as an input, it must have at least 2 volts. But how about the low state? The output must remain below 0.8 volts in order to maintain a solid low state. So there is quite a lot of error margin here, or safety margin in a standard TTL logic. So we have the uh, 0.8 volt low state, so anything between 0 and 0.8 is low, and then the anything between, maybe I should just, since I have pen and paper, sometimes it's much better than the those electronics. So somewhere here we have VCC, here we have 2 volts. Well, this is 3 volt system, evidently 0.8 volts. This is low state, this is high state, this is any state. So that part, you shouldn't let the output float in between these voltages. It's undefined. So basically, if you are running from low to high signal, it should go rapidly like that. From high to low, basically you should drive it like that as fast as possible through that undefined region. So that's how the logic circuits actually should work. Most of the problems on this data transmission are happening because of that gray area. It's then if you have even a small amount of noise, you can start getting extra triggers and such kind of things. But anyways, back to this problem. So in order to maintain a solid low state, the output must remain below 0.8. Okay. Now the question is what is the maximum current the device can sink and still maintain low state? Meaning that if you sorry about that spider on my screen. On this picture, you determine the maximum current and minimum corresponding minimum the resistor, so that when you are driving low state, which basically should mean inside of the processor that this Thevenin's model voltage goes to 0, but the output resistance may be actually the same. To make this one totally correctly, you should do those measurements again. However, actually what I found out is by testing it, the model inside of that simulator actually have a symmetric drive for the sourcing and syncing. It means that, well, just to save some time, you need to do it this by doing using the theory. Anyways, so determine what is the maximum current the device can sink and still maintain the low states and corresponding minimum load resistance. Remember to explain again. It doesn't hurt if you go and also test it with the simulator. Test this maximum current and minimum resistance in simulator. Okay, snapshot of the Tinkercad. Okay, it's a snapshot of your design. Design means almost always your Tinkercad picture. Okay, third part. Okay, Arduino I/O and LED. Determine what size current limiter resistor is required for Arduino I/O to drive a red indicator LED. if somebody is thinking of why it should be red, not green or blue. Okay, in reality, in real life, the LEDs actually are different. Different color has different voltage drop for the same current. It's just plain physics why it's that way. Couple of weeks from now, actually, I will explain why it's that way. Next week is dedicated on circuits, but is dedicated to the AC circuits. Then we on the fourth teaching week we go to and check these the integrated circuits, how or semiconductors, and a little bit about integrated circuits. Okay, so measuring the voltage drop of LED as a function of forward current between 0 to 20 milliamps. 20 milliamps is usually the maximum current you should put through this kind of indicator LEDs. On white LEDs actually can withstand, well, they are usually driven at the maximum safe current if you are taking white LEDs for lighting the applications. But signal LEDs, usually it's 0 to 20 milliamps. There are also some smaller ones that are from 0 to 4 milliamps only. But anyways, most of the say signaling LEDs are withstand 20 milliamps. And there, how to do these measurements first is to actually use variable resistor to adjust the current. I can actually show you some hints how to do it. Then next one is making a graph. I don't care how you do the graph as long as it's actually have the voltage drop on horizontal axis and current on the vertical axis. And what I'm expecting to see is a graph which looks a little bit like that. I haven't tested that yet myself, how it would look like, but this is how a typical LED actually, the current versus voltage looks like. So it's partly exponential curve. This is not exactly exponential, so basically from that point to there it's exponential, but before that it's something else. So okay, so expecting to see that kind of curve, and then using that curve or your measurements, determine theoretically what is the minimum size current limiting resistor value when Arduino IO pin is driving an indicator LED, and we want to limit the maximum pin output current to 10 milliamps, so not to the full 20 but 10 milliamps. Why 10? Arduino actually have those now I should actually show something on Tinkercad. I will just take this Arduino Uno there. Ooh, there's a new component, microbit component. Arduino Uno. It has these digital I/O pins from 0 to 13. Then it also has 6 analog in pins, which also can be used as digital outputs. Okay, depends how you modify it. It has total 20 I/O pins. Just in case you are putting all of those pins are driving an LED with that 10 milliamp maximum current maximum pin output it's then the full total current is then 200 milliamps, which is exactly the same as the total maximum current of Arduino Uno. So that's why you are shooting for 10 milliamps, just in case. It's a good idea to actually have an average value. If none of the outputs never exceed that average value, then you are on safe margin on your always with your design. Okay, so that's why. And again, snapshot. All right. By the way, there's that snapshot. When it says 0 points for the entire exercise, it means the entire part of the exercise. So it's the snapshots, when they are marked like that, it means that you need to put the snapshot of the circuit there. So that's just, just for seeing what kind of designs you make, and then basically we can give you some comments on how to improve them. Okay, so the first part, again, it was about making these theoretical calculations using the theory and compare with the measurements of the first exercise. Then the second one is circuit analysis of Arduino I/O, and there we have the Arduino pin, and actually just putting a resistor here. There, like that, and connecting it either to the pin. Oh well, it always goes to the pin, but either the ground for the high state, or then there's that five volts terminal here. Okay, that's how you do the basically the 5-volt test. So for the low state, and then of course you need the voltage meter somewhere. Where is my voltage meter? Looks like multimeter is somewhere else nowadays. Okay, so putting a multimeter here, doing the measurements, voltage or current, depending on the exercise. And then practically you need to also make a code to run it high. One way to start the whole thing would be, there are these examples. Examples, Arduino or starters. There is a blinking light. Which might be a good place to start, since it already have an LED or the register LED that you can actually remove from there. But anyways, it already had the code. Although, oh, wait a minute. Shouldn't there be? Ah, okay, there. As me and Juho have already told you, you cannot use the code. Just these blocks. So you are ICT engineers, you should be writing the code, not playing with the Lego blocks. Unless it's educational, of course. Lego blocks are actually the best. But that kind of code blocks, I'm not too fond of those. They make things confusing. Okay, so practically you can start from that kind of design. There you have the pin modes correctly set, and then you have this digital write high here, some delay. So how to make sure that you have the system staying high, how about just commenting the other when it goes low, okay, and changing the pin numbers, that kind of things. Very simple things to do. And then basically, yes. So, do you have any questions of this exercise 3? Okay. I will stop recording then.